We showed that in our previous modules the concept of point estimate for a population mean. And we had said that the point estimate for a population mean is simply nothing more than just taking the average of a sample that we have, and it is a good estimator of the population mean. This point estimate will most likely not be the exact population mean, but it will be close. The error might be slightly above or slightly below, but not too far away. There's really going to be no indication that it's going to be more or less. It's just a random chance that it is a little bit higher or a little bit lower. In addition, since the data comes from a normal distribution, it might be safe to assume that there's an equal chance of error above or below, making the range symmetric or balanced. Here we have a chart where we have the mean of a sample as denoted by this X bar and this red bar, and an error could be above or below. The equal value of the error on both sides of the mean is called the margin of error. It is the approximate amount above and below the mean where the population mean would land. So regardless of the point estimate used, a sample mean or standard deviation, it could be written as point estimate plus or minus margin of error. More specifically, for the sample mean, X bar plus or minus this margin of error. So the population mean will fall within this X bar plus or minus the margin of error. As we said before in a previous slide, the sampling distribution was shown to be normally distributed. Either we knew this or we can infer it through the central limit theorem. If the sample distribution follows this, we again can show that 68% of all the means from the samples will fall between plus and minus 1 standard deviation, 95% will fall between plus or minus 2 standard deviations, and 99% will fall between plus or minus 3 standard deviations. Specifically, 95% of the data falls just short of 2 standard deviations and is really 1.96 standard deviations. So this is a concept that the actual number is not really going to be 2 for 95% exactly. It's going to be 1.96. And you could compute that if you wanted to by going into Excel and putting norm.s.inv 0.975. The reason I do 0.975 is because 95% means that there's 5% that's distributed between the two tails. So what you want to do is you want to make sure you divide that by 2, which we would say is alpha over 2. And so you would end up with 0.975 because it's 2.5% in both sides. Remember that the norm.s.inv will be from the point on the right and give you the distribution all the way to the left. So that computation is going to end up giving you the 1.96. The margin of error, again, is this formula of the standard deviation of the sampling distribution, which is equal to sigma over the square root of n. This can be written again as 1 times sigma over the square root of n. The goal is to find an area where 95% of the sample means fall. Then the area would need to be multiplied by 1.96 and not 1. This 95% area would provide a significant confidence that 95% of all sample means would be in this area. This 95% or 0.95 is called the confidence coefficient. The margin of error can therefore be more accurately denoted equal to 1.96 times sigma over the square root of n. More importantly, the full interval around the sample mean can now be written as X bar plus or minus 1.96 times sigma over the square root of n. The 1.96 again is obtained from the z-score that had a 95% area around the mean. 95% is the confidence interval, 0.95 is the confidence coefficient. Using the confidence level at 95% with a z-score value of 1.96, a confidence interval can be given using the formula, as we said, X bar plus or minus 1.96 times sigma over the square root of n. The formula above provides that confidence interval, an area with a lower bound and upper bound equally around the mean, represented by the right side of that plus or minus side. Assume a sample of 100 is taken with a sample mean of 72 and a standard deviation of 7.5. We could then use that information to create the confidence interval. X bar, which is our average, so that's going to be 72, plus or minus 1.96. Again, this is our z-score value for that 95% confidence interval. We have S over the square root of n. We're going to use that sample standard deviation because we don't know what sigma is. We divide it by the square root of n, so we end up with 7.5 divided by the square root of 100. That gives us 72 plus or minus 1.96 times 0.75. That ends up being 72 plus or minus 1.47, which gives us 70.53 to 73.47. So therefore, our confidence interval goes from 70.53 to 73.47. And you could see that that would be equally distant from the left and to the right of that mean of 72. So 72 is right in the middle of that. A closer look at the 1.96 yields a very interesting point. Recall that we used the 95% area of a standard normal distribution and demonstrated that this was a z-score of 1.96. So we had x bar plus or minus 1.96 times sigma over the square root of n. Since it comes from a standard normal distribution, this is known as the z-distribution. Thus, the formula is more accurately written as x bar plus or minus some z-score or z-multiple alpha over 2 times sigma over the square root of n. The alpha over 2 is the parameter for the z-distribution, or the area required. Note that if the 95% is desired, this means that 5% remains equally distributed around the tails, meaning 2.5% on each side. The 2.5% on each side is seen in the distribution here. We can see that to the left and to the right, we have 2.5%, which would give us our 5%. Plugging this into Excel, we do the norm.s.inv of 0.975, and that yields 1.96. Now, we can obtain other confidence intervals in a similar fashion. Again, using that formula up to the right, a 99% confidence interval would make the z-value norm.s.inv 0.995. Again, our alpha is 0.01, so we're going to cut that in half, and that will give us 0.005. And that basically gives us the norm.s.inv of 0.995. That norm.s.inv of 0.995 yields 2.58. A 90% confidence interval would make the z-value 1.64. So to note, a higher degree of confidence requires a larger margin of error, making the width larger. So a higher confidence level is going to be a wider interval.